Okay, so welcome everybody. It's my pleasure to introduce Florian Russold, who will talk about learning from two-parameter persistent homology using Graphcodes. Please take it away.
Thank you very much. So I will talk today about a new method of how humans as well as machines can learn from two-parameter persistent homology. So I'm assuming that everybody in this meeting is very familiar with persistent homology, but in case some viewer is not familiar, I will do a short review of a typical one-parameter persistent homology pipeline, just to set the stage and to see how we progress from here to two-parameter persistence and what are the issues and how we deal with them later. So a short review. So this is like an example of a one-parameter persistent homology pipeline, where the goal is to extract topological features from a dataset and use them as in a later machine learning pipeline. So it goes as follows. We start with a set of data points. So in this example, they are sampled from an analysis. We kind of model this data set by a scale-dependent family of simplicial complexes. This I will call in the following a filtration, a one-parameter filtration. So this filtration kind of captures the shape of this data set at multiple scales. And we now want to summarize the topological or some of the topological information in this filtration by the persistent homology. So applying the persistent homology to this filtration, we obtain what is called a one-parameter persistence module. And such a one-parameter persistence module, it can be viewed as a diagram of vector spaces and linear maps, can be faithfully summarized by a persistence diagram. So each point in this diagram describes the lifetime of a topological feature in this filtration. And I've put this isomorphism symbol here to note that this is actually a complete description. So this persistence diagram faithfully captures the persistent homology. So we've now extracted these topological features from this data set, but to use it in, for example, a classification task, we somehow need to get this to the standard data analysis or machine learning workflows. And the problem is that most of these workflows, they kind of operate on Euclidean space. So we kind of have to turn this thing into a vector in Euclidean space. But to achieve this, many methods have been proposed, and they are usually called vectorization methods. So this is, for example, a persistence image. This is kind of a vector representation of this persistence diagram, and this we can then use in a machine learning workflow. And of course, there are other ways to use persistent homology, but this is actually a very typical workflow that has been applied in many cases. So one interesting alternative to this vectorization I talked about at the end is what is called Pursley. And this is actually a method that kind of circumvents an explicit vectorization and operates directly on the persistence diagram. So instead of turning the persistence diagram into a vector by some handcrafted vectorization method, this Pursley architecture, it's actually a neural network architecture, it eats the persistence diagram directly as a set of vectors. And it is based on what is called a so-called deep set neural network architecture. So of course, this thing also computes a vectorization implicitly internally, but we don't have to predefine the vectorization. The learning how to compute the vectorization from the persistence diagram is actually part of the process. And I just put this here because that will be important later. So this is the one-parameter persistent homology, and it has been applied many times, very successfully, but it also has various problems. And probably the biggest problem is if we have a data set that is kind of infested by outliers or noise, like we can see here, for example, then this can destroy our whole pipeline because the persistent homology is actually very sensitive to outliers and noise. So if you look at the uppermost column in this bifiltration here, we see that a few outliers in the middle can completely wreck our hole in the middle here. So persistent homology is sensitive to outliers, but people have invented ways to deal with this, namely multiparameter persistent homology. And in multiparameter persistent homology, we deal with the outliers by additional to this scale parameter, we introduce other parameters. For example, we can filter the points also by some density measure. This is what I actually did here. So if we pick the right density threshold, we can see this hole here very nicely. But of course, we don't know beforehand what is the right threshold for the density. So that's why we have to deal with the whole bifiltration. But the whole bifiltration, it nicely captures how the kind of the shape varies as we vary the density and the scale parameter. And taking again the homology of such a bifiltration yields what is called a two-parameter persistence module. But the critical thing here is if we go from one parameter to two parameters, we kind of go through some critical phase transition, where these persistence modules, they turn from relatively simple to wildly complicated objects. So it is known that for two-parameter persistence and more parameters, there does not exist a discrete complete invariant like the persistence diagram in the one-parameter case. But people have invented various incomplete invariants, like for example here we have the rank invariant, that captures some partial information of the persistent homology. And also many vectorization methods have been generalized from 1 to 2 parameters and even more parameters. But these vectorization methods are now based on this incomplete invariance. I've used the same picture here, but to give you an example, the multiparameter persistence landscapes, they vectorize the rank invariant. But we can do this, and then we can feed these vectorizations to some machine learning workflow. So the pipeline is basically the same as in the one-parameter case. The only difference is that here we don't have this isomorphism, but we kind of lose information by going to some incomplete invariant. And so the question we ask now is there some way to kind of circumvent this vectorization of incomplete invariant step? Is there some way to get directly from this two-parameter persistence module to some machine learning workflow? So we could maybe rephrase these questions. Is there some way of generalizing this Pursley architecture from the one-parameter pipeline to two parameters? And the answer is yes, there is a way. And the way we do this is by using the so-called Graphcode representation of two-parameter persistence modules. So in this kind of cartoon, I want to give you the general idea of the Graphcode representation, but I will go into more details later. So suppose we have this bifiltration here, which is here illustrated as a grid of simulation complexes we've connected with inclusions. So we can take kind of an alternative perspective. Instead of a two-dimensional grid, we can view it as a sequence of one-dimensional slices. So if you forget about the arrows in between and just focus on the slices, then each of these slices is just a one-parameter filtration. And as we heard before, we can compute the persistent homology and summarize it by a persistence diagram. So here we have the persistence diagram of each of these slices, of the homology of each of these slices. So that's nice. So the kind of this collection of persistence diagram, it's even an invariant of this two-parameter filtration. But of course, it does not capture the whole content of the two-parameter persistent homology because we are missing of how these slices are connected. But in homology, but we don't only have the slices, we also have these inclusions of slices. So this one-parameter filtration includes into this one-parameter filtration, and so on. So if we take the homology, we actually get an induced map in persistent homology. So the persistent homology down here maps to the persistent homology up here. And we can summarize these maps actually in a faithful way by edges between these points in the persistence diagrams. And I will go into more detail later, but intuitively, if each feature down here, it's kind of represented by a persistent cycle. So you can actually find a representative of this kind of feature here in this filtration. And these edges just track to which persistent cycles a cycle down here maps if you go up here. So these edges between these features, they're just a representation of these maps in homology. And I think I forgot to mention this. I'm considering set 2 coefficients here. This is actually not really a restriction because you can also label kind of these edges by some scalars, but just for the sake of simplicity, we assume set 2 coefficients. So this graph here, and it's actually an embedded graph or a labeled graph, because each of the vertices here has coordinates, namely the coordinates of the point in the persistence diagram. And this graph, vertices plus the edges, is actually a complete description of the two-parameter persistent homology. But careful, it is not an invariant, because only the persistence diagrams, so the vertices are invariant. The edges, they kind of depend on a choice of bases in each slice. So it is not an invariant, but it is complete. It captures all the information. And we call it the graph code. It doesn't work so nicely with the persistence diagram, but it's like the combination of the word barcode and graph. That's why we call it graph code. Okay, so I now have constructed this representation and it captures the persistent homology, but you might ask, so what? So why is this useful? And it is useful by combining these graph codes with so-called graph neural networks. So I'm not assuming any prior knowledge on graph neural networks, so I will explain how this neural network architecture can take graph codes directly as an input and kind of process them. So this is the way how we circumvent the vectorization by computing this graph representation, this labeled graph representation. So we have this graph code. It's kind of a layered graph where the edges flow up. And each vertex is labeled by its coordinate in the persistence diagram. So it has like a birth def coordinates. And now this graph can be directly input to this graph neural network. And the way such a graph neural network processes these graphs is it pushes it through different layers. So for example, we have here 4 layers, and the graph comes to the first layer, and each vertex has some vector attributes. And now in each layer, these vector attributes of the vertices are updated. And the update rule works as follows. So if we focus on this red vertex U here, it has these birth def coordinates, and now we want to update it. And the update works as follows. You look at all the neighbors of U in this graph. It's like these blue neighbors here. You kind of aggregate these vectors to this U. This is also called message passing. So these layers are called message passing layers. So it aggregates the information of its neighbors, maybe through some differentiable function. You can also have information on the edges that are taken into account here. And then you take the label of U and the labels of its neighbors and again apply some differentiable function. And then you get a new vertex label. And this happens in each layer. So in this way, you kind of update each vertex by a neural network, but you also aggregate, the vertices also communicate with each other through the graph structure. So in this way, this graph neural network takes into account the graph structure and the vertex labels. And after you go, yes?
I had a question. So if I understand correctly, you put the whole graph code into the GNN layers, right?
Exactly, yes.
The point is that I don't understand exactly what is a vertex, because I will have guessed that you need the birth and death time, but also which scale, right? Because every vertex in the graph code has also a scale.
Yes, exactly. We actually actually you don't really need this. So a graph neural network can take any graph as an input.
Okay.
Theoretically, you don't need this, but we actually keep this information of the height of a vertex also. So I was about to mention this in this step.
Sorry.
So
okay.
we keep, I should have put this here, you're right. But we also keep like the height of the vertices and we process them there. And we end up like with the same graph, but different vertex attributes. And now we apply what is called a pooling layer. And here we use kind of a local pooling where we pool each height separately. And in this way, we take into account this additional information of the graph codes of the height. So we get from each height level, we get a vector and we concatenate them. And in this way, the graph neural network computes the vectorization out of this graph code. But these functions here that process these graphs, they are learnable. So these are like, these functions here are actually neural networks, like the ones that you see here. But after we compute this in this internal vectorization, then we can just push this vector through additional dense layers, or people also call them feed-forward layers, so just a standard neural network, and then we can do whatever, classification, regression, whatever. So this is our idea of an architecture that processes these graph codes, but it could be different. So every graph neural network would be fine. And I'm sure experts in machine learning can find better ways. But now, together with this, so the graph codes plus this graph neural network architecture gives us a way to actually find this circumvention of the incomplete vectorization. So we can now directly go from the two-parameter persistent homology to the graph code. And here I should have again put this isomorphism sign, because from the graph code, we can reconstruct the two-parameter persistent homology up to isomorphism. So here we have this complete summary, and then we just feed it into this machine learning pipeline. And so I've now hopefully convinced you that that's something you can do theoretically, but of course you might wonder, does this actually work? And as a proof of concept, we've conducted actually several experiments, but this is like my favorite one. And what we did in this experiment is we generated a data set of point clouds. So each instant is a whole point cloud. And we create these point clouds by randomly generating a shape configuration, as you can see here. So here we have 2 annuli and 3 disks, but we kind of randomize this, so their size and where they are placed is different. Then we uniformly sample from this shape configuration, and then we add uniform noise to the whole thing. And the final instance you can see here. And now each instance is labeled with the number of annuli in the underlying shape configuration. So in other words, each instance is labeled by the rank of the homology in degree 1. Because this shape configuration has rank 2 in H1. And that's the label of this class. So now the task is, if you only see this point, probably as a human, you could still see that there are like these 2 annuli. And the task is to predict this. So you get these point clouds, and actually from these point clouds, we compute a density alpha bifiltration. Then we compute the persistent homology. And then we computed all kinds of vectorizations or other forms of representation of this two-parameter persistent homology. And then you can learn a little bit on a training set, and then on an unseen test set, you have now to predict the homology in degree 1 from these instances. And as you can see here in this table, the Graphcodes, the GC, did very well on this synthetic toy dataset. And what you can see here is, for example, multiparameter persistence images, landscapes, ordinary persistence images. These are the generalized rank invariant landscapes. This is Hilbert signed measure convolutions. And this is, again, the Graphcodes. And what we also tested is the GC and E are the Graphcodes with the edges removed. So this test has the purpose to show that the edges of the Graphcode actually yield additional information. And as you can see here, a lot of information is already contained in the persistence diagrams of the slices, but the edges give you an additional 4%. And since the accuracy of maybe 83% is already high, gaining an additional 4% can be actually quite a lot. And what you can also see, so this line I should have mentioned, is the average prediction accuracy in percent. And what you can see here in the second line is actually the time required to compute these representations. And maybe here, the difference is even more notable, because you can see here that the graph codes are actually computed much faster than let's say, most the other vectorization methods. You can see here, for example, the multiparameter persistence images take 100 times as long as the graph codes. Okay, so maybe this synthetic data set already convinces you. We also did other experiments, but actually on this data set, it did the best. So just as a disclaimer, maybe that's a little bit of cherry. Okay, so hopefully I've convinced you that the graph codes are actually a valid idea to explore. And now I want to dive a little bit deeper into the theoretical construction of the graph codes. So how do we actually get this graph, and why is it a complete description? So to explain this, I actually want to start with a special kind of a two-parameter persistence module, as you can see here on the upper left. So this is a 2-parameter persistence module that is of the form like, here we have 4 by 2. So it has only one step up, but this just serves an example for an n times 2 persistence module. But the point is, I want to look at, these are often called ladder modules. So I want to look at 2-parameter modules that only have one step up. Because these kind of 2-parameter persistence modules can also be viewed in a different way. Namely, we can view them as maps of 1-parameter persistence modules. So you can think here you have a 1-parameter persistence module down here. And here you have a 1-parameter persistence module up there. And these vertical arrows, they just define a natural transformation or just a morphism of persistence modules. And we know that each 1-parameter persistence module is isomorphic to a sum of interval modules. And I've already picked the basis here in the right way, such that we have here an interval module, and here we have a direct sum of 2 interval modules. Here we can see the same picture in a little bit of a different way. Here I just illustrated the intervals. So we can always decompose each of these slices as a sum of interval modules. And now, after we get this decomposition, these matrices actually describe how each interval maps to the intervals in the next layer. So what we can actually do is we can represent this whole thing here by a single matrix down here, where the columns and rows are labeled by the intervals. So we have here an interval 2, 5, that's the down one, and it maps to both the interval 1, 5 and 2, 4 up here. And in the small print, I've also put the algebraic reason why this is always possible. And so the reason is if we have two 1-parameter persistence modules, we know that they're isomorphic with sums of intervals. So we have here maps from m to n is the same as maps from the sum of intervals to the sum of intervals here. And if you have like finite direct sums, this is just the same as all maps between individual summands. So this is basically the reason why matrices exist. So you can always factor each map into maps between the individual summands. So that's the first observation. And the second observation is if you're down to maps between individual summands or individual intervals, then there's actually only one non-zero map up to isomorphism between two interval modules. So actually you can describe a map between two intervals just by a scalar. With Z2 coefficients, it's either 0 or 1. There are no other maps. So this matrix with these two 1 entries fully captures this picture here. And an alternative way to just represent this matrix is with this graph. For each column and row, we make a vertex, and we just view this entries, so this matrix here, as an adjacency matrix of a bipartite graph. So here we have this vertex here connects to both vertices up there. So that's basically the reasoning for this special kind of 2-parameter persistence module. But now we can just straightforwardly generalize this to arbitrary persistence modules. So if we now look at a more general 2D persistence module, so this grid of vector spaces and linear maps, we can again change perspective. And alternatively, we can view this as a persistence module of 1-parameter persistence modules. This is just a trivial categorical equivalence. We can just view this as this 1-parameter diagram here, where each of the objects is itself a 1-parameter persistence module, and each of the arrows here is a map. And now we again apply the second observation, namely that each 1-parameter persistence module is isomorphic to a sum of intervals. So I just add these isomorphisms here. So here we have the sums, here we have the isomorphisms, and of course this map factors through these sums. And the thing here is now, this sum of intervals is unique for each slice, but this isomorphism is not. So the summands here, the intervals are unique, but for the isomorphisms, there are choices. And that's exactly the reason why these graph codes are not an invariant. And we call this collection of isomorphisms here a barcode basis of M, because it kind of gives you this isomorphism from a 1-parameter module to this sum of intervals. But after we have this isomorphism to this sum of intervals, we can now do exactly the same thing as we did before. Namely, we describe each of these maps as a map between individual summands or intervals. And we represent these maps by these matrices. And that's like a fateful representation. And if you now have these matrices, you can just view them again as adjacency matrices of bipartite graphs. The vertices are given by the intervals here. So each interval labeling a column or a row gets a vertex. And we just connect two vertices in adjacent layers if there's a one entry. And this gives us exactly the Graphcode representation, depending on a choice of barcode basis. And of course, you don't necessarily have to view it as this graph. You can also view it as this sequence of matrices. And I also like this perspective because basically you've brought down the 2-parameter case to the 1-parameter case, or kind of a 1-parameter case, because a 1-parameter module is just a sequence of matrices. And you have exactly the same thing here. The only difference is that each column is now not just a one-dimensional vector space, but now it's like an interval module. And if the time allows it, we will actually get to why this matters later. But now we've theoretically constructed this graph code. And now I want to get into how do we algorithmically compute this from bifiltrations. And so our algorithm actually works on general minimal presentations, but just for the sake of argument, I will explain it for one critical bifiltered simplicial complexes. So we consider again a two-dimensional bifiltered simplicial complex, which is here represented by this two-dimensional grid of simplicial complexes and inclusions. So if we now want to compute the graph code, we at first need to compute the persistence diagram of each slice. And the naive approach of this would just apply the persistence algorithm to each of the horizontal slices. And this would cost you like a number of slices, which is here S times n cubed time. And the edges, you can actually, so computing the edges is basically expressing a cycle down here in the basis of the cycles in the slides above. So that's also kind of a linear system problem. So that's also n cubed. So in the naive way, you can also compute you can compute the complete graph code in O of S times n to the power of 3. But this is actually not optimal. And what we do instead, and what we call the graph code algorithm, is we start down here with an empty boundary matrix, and we kind of add the boundaries, or the simplex boundaries, which are the columns of this boundary matrix, in batches. And in each batch corresponds to the simplices that appears first in the teeth slice of this bifiltration. So for example, the first batch is just the lowest slice. The second batch would be all the simplices in the second slice that are not already in the first slice, and so on. So we add these columns in these batches, and after adding each batch, we reduce this matrix. And if we add the next batch, we reduce it again. So at first glance, that sounds like we do basically the same thing, but actually when you do it in this way, then cumulatively, the number of operations you do in this reduction is the same as if you would reduce the biggest slice up here from scratch with the 1-parameter persistence algorithm. And the edges can also be computed on the fly because the edges can actually be read off from the basis transformations you have to do to reduce the matrix after adding the teeth patch. Because kind of adding the columns from left to right, so the change of the basis elements actually encodes how the basis elements change if you go from one layer to the next layer. And so with this refined method of computing the graph code, we can actually do it in O of n to the power of 3. I forgot to say if n is the size of the bifiltered simplicial complex. So in this way, we can actually compute this graph code in the same time as we would be able to compute the 1-parameter persistent homology of the biggest slice. One additional thing that we leverage to make this computation much faster is what we call compressed graph codes. So one problem with this algorithm, although you can do the reduction fast, it is actually very costly to kind of maintain this graph because the graph can get very big. But actually, most of the vertices that you see coming from bifiltrations in practice, you actually don't need them. because it is very common in these graphs that you have long paths along which the intervals don't change, as you can see here, for example. And what we do with the compressed graph codes, if we see such an isolated path along which the intervals don't change, we just compress them into a single edge. So we remove all these vertices and replace this whole path by this single edge. And this way of compression, I won't explain in detail how it works. Basically, the way you get this is you can compress, you can kind of collapse down a vertex from here to here if it is the unique successor of its previous vertex. So you can remove all of them, you can remove these, and you can remove these, but you cannot remove this one because it is not the unique successor of this one. But this way of compression actually preserves all the information of the graph codes. So you can actually reconstruct the initial graph code from the compressed graph code. So there's actually no loss of information. And this actually significantly reduces the size of the graph codes and also significantly improves the computation time. And this I want to demonstrate you in this next slide. Here we just have various instances from which we compute the graph codes. Here you can see the number of generators and relations in the minimal presentation. And here you can see the number of vertices of the compressed graph code and the uncompressed one. And you can see that the compressed graph code contains like orders of magnitude less vertices than the uncompressed one. And you can also see that the time to compute the compressed graph code is like orders of magnitude smaller than the uncompressed one. And what you can also see is that actually the number of vertices in the compressed graph code is kind of the same order of magnitudes than the minimal presentation. It's kind of a factor of 2 bigger, but it's like the same order of magnitude. And finally, what you can see here in this table is actually claimed in my abstract that graph codes can be computed as efficiently as one-parameter summaries. And as to prove this claim, we have here in the last column the computation time of fat to just compute the one-parameter persistent homology, just of the biggest slice, so of the whole complex, but in a one-parameter filtration way. And you can see that the times, they're kind of the same order. So it's almost the same for the compressed graph code and the fat. So this hopefully convinces you that indeed these compressed graph codes can be computed very efficiently. So now I want to come back to applications of graph codes. And I've already spoken about our main application of using graph codes to learn from 2-parameter persistence modules using this graph neural network pipeline. But finally, at the end, I want to demonstrate you that also not only machines, but also humans can learn from this graph code representations by giving a new criterion for interval decomposability of 2-parameter persistence modules, and to show that these graph code representations are also very helpful in decomposing 2-parameter persistence modules into summands. I will actually start with this part. So consider a graph code representation of some 2-parameter persistence module. Suppose it is the one that is shown here on the slide. And as you can see, this graph here has 4 connected components. So the graph code is kind of the union of these the disjoint union of these 4 components. And I've mentioned in the beginning that the graph code is an equivalent representation of the persistence module. So from this graph code, we can actually reconstruct a 2-parameter persistence module. And if this graph code decomposes into 4 components, then the persistence module this graph induces is actually a direct sum. So being a disjoint union of components implies that M is isomorphic to a direct sum, namely the sum corresponding to each of these components. And this proposition here is a little bit vague. I don't want to get, for time reasons, into the technical details of this result, but you can actually show that components of this graph and sums of the modules, they're kind of correspond to each other. So why is this useful? Because what you can see here in this table, we have again some instances from which we computed graph codes. And we have here the number of indecomposables of the modules. So for example, this This instance has 4,284 indecomposables. And here you can see the number of components of the graph code representation. And this is just the generic graph code representation that our algorithm computes. And as you can see, that this graph codes usually have a lot of components. Like without doing any decomposition, just the generic representation already decomposes almost completely. So this is very interesting because we can also go back and forth between like presentations and graph codes. So what we tried here is we tried to apply some recent decomposition algorithm on these graph codes. And when I say on these graph codes, I actually mean on presentations that we extract from these graph codes. And so we have here the comparison of applying this decomposition algorithm to the graph codes and to the input directly. And as we can see here on some instances, this actually speeds up the computation. So actually, if we compute the graph code representation and then kind of turn it into a presentation and then do the decomposition on that, this is actually faster than doing the decomposition directly. But it's not consistently better on all instances, so it varies a little bit. But on some of them, it's like here, for example, 25 times faster. So this is a very unexplored area, but we just observed this in our experiments. So graph codes might be useful for decomposing modules. And in the last 5 minutes, I now want to go into the maybe second main application of graph codes so far, namely deciding if a two-parameter persistence module is interval decomposable. So a short introduction to two-parameter interval modules. So if we have a two-parameter module, like here, this grid of linear maps and vector spaces, an interval module is just a module that has like one-dimensional vector spaces and identity maps supported over some convex and connected subset of this grid poset. So a convex and connected means here in the sense of posets. So you can see, for example, this thing here is an interval module, and it's supported over this region that is bounded by lower and upper staircases. This is, of course, a little bit of an informal definition, but it's basically it. And an interval module, at least with these two coefficients, is completely determined by its support. So the support region here completely determines our interval modules. And the interval modules, they're kind of the generalization of the intervals or the bars in the one-parameter case. And we call a two-parameter persistence module interval decomposable if it is a direct sum of interval modules. So if M is a direct sum of these three intervals, then we call it interval decomposable. But of course, the difference to the one-parameter case is that not every two-parameter persistence module is interval decomposable. For example, we can see here the example again I showed previously, and this one is, for example, not interval decomposable. So we can look at a problem that given M, decide if it is interval decomposable, and if the answer is yes, then compute the intervals in this decomposition. And in the following, I will show that the graph code representation actually gives us a very nice algorithm, at least a very nice conceptual algorithm to decide this interval decomposability. Because what we can observe here is that we have a two-dimensional interval module. The graph code representation is actually just a path of one-parameter intervals. So for a 2D interval module, the graph code is always an ascending path. And this is actually a result. So you can show that if the graph code is an ascending path, then it is an interval module. And conversely, if you have an interval module, then its graph code is always an ascending path. So in this case, there's actually no choice for different bases, because in some sense, you only have one basis element in each slice. So we can actually characterize the interval modules by their graph code representations. And if we combine this with the kind of components proposition from before, then we get the following theorem, namely that a 2D persistence module is interval decomposable if and only if there exists some barcode basis such that the graph code representation with respect to this basis is a disjoint union of ascending paths. In this picture, you see, for example, a sum of 4 intervals, and its graph code representation is this union of ascending paths. I now tilted it. And that's an if and only if. So basically, this gives us a very nice characterization, but it also gives us an algorithmic strategy. Because if we look at a graph code representation that is not already a disjoint union of ascending paths, so you see here this edges are a little bit entangled. So now the question is the module induced by this graph code interval decomposable? And I've also represented it by the matrices up here. So what we can do now is we can sweep this representation from left to right and try to untangle these edges, to kind of untangle it into a disjoint union of paths. And because the time is already over, I just show you how this works. So if you slowly go through this, then you start kind of modifying these matrices. And actually, the way you modify these matrices is by changing the barcode basis. It's kind of changing the basis of a vector space, but not quite, because now we don't have one-dimensional vector spaces, but interval modules. And the operations you can do on them is restricted by the intervals. So you can only add to intervals if they lie in the right way with respect to each other. But if you try to apply these operations, you can finally untangle these paths into a disjoint union of paths, and on the one hand, you've decided that it is interval decomposable, and you've also found the intervals. And the remarkable thing is, if under the condition that the intervals in each slice are different, so there are no two same intervals in the same slice, then if you follow this, if you try to kind of reduce these matrices to kind of this normal form, or you try to untangle these edges, if you get stuck at some point, then you can actually decide that it is not interval decomposable. So if you want to go into more details of this algorithm later, I'm happy to do that. But for time's sakes, I just showed you this once. Maybe I show it twice. So you just go over this and you remove edges, change edges until you end here. So this gives a very nice conceptual algorithm for computing the interval decomposition, because if you think about it, it's actually exactly the same algorithm as for the one parameter case. If somebody presents you with a persistence module in the form of a sequence of matrices, the way you would efficiently compute the intervals is you would sweep through these matrices and transform all of them to this normal form. And after you found this normal form, then you have the intervals. And that's the same algorithm. It's just that the operations you can do is a little bit different, and therefore you can get stuck. And then it's not interval decomposable. I will end with a little bit of future work. So the major goal for future work is actually to improve this machine learning pipeline for graph codes. Because one of the main issues is that the edges of the graph code, they're kind of not unique. So it's not invariant, so the edges just depend on choices. And that's, of course, a little bit of a problem, because you might get two different representations of the same instance, and it might give you a completely different output. I mean, you can see that in practice, it still kind of works, but of course, that's a problem. And there are some plans how we could deal with that. Namely, because we're already in the realm of machine learning, we can actually provide these machine learning models different representations of the same instance. So we can actually change this barcode basis and provide the model different representations, and in this way teach the model to kind of identify different versions of the same graph code. Because for a human, it's very easy to extract like the persistence module from the graph code. So all the information is there. So we assume that with the right kind of learning pipeline, that this can also be achieved by machine learning models to some degree. So that's our major goal. Another interesting path is to develop heuristics for the decomposition via graph codes. So what you find when you compute these graph code representations is that most of the graphs are actually simple. So you already find many components, and even most of these components, they are very simple. Actually, many of them are actually intervals. But many of them are also not quite intervals or not quite paths, so to say, but they have a few branchings. But you can very fast, you might be able to check very fast if you can decompose this further by just doing a few checks. So, and by applying these heuristics, you might even find more components very fast. And the third, maybe more theoretical goal is we've seen that we can characterize the interval modules by these ascending paths. And we want to investigate if there are also other families of indecomposables that can be characterized by graph theoretic properties of their graph code representations. Okay, and so that's it from my side. And if you're interested, we have 2 full articles, and they appeared in Europe's 2024. So the first one actually contains the machine learning content, and the second one is currently under review, and it focuses more on the theoretical parts and on this interval decomposition algorithm. Then thank you very much for your attention and for having me.
Thank you very much, Florian. I will ask everybody to unmute themselves and clap for the speaker. Are there any questions who wants to stay on record? I will try to look for a raised hand, but in the meantime, while people maybe warm up, I'm pretty sure you see that coming. But so, what is exactly the difference between a graph code and a vineyard? Because vineyard is untangled, right? If I understand correctly, that in a graph code you allow points to match to multiple points, I mean as vector.
Yes,
but
exactly.
In a vineyard, you will not allow, most of vineyard will not allow the crossing of path, which means that you cannot join things. Is my understanding correct?
Yes, exactly. So I'm also sometimes confused about what is the definition of vineyards. Because
yes.
I think I've heard people use it also in a different way. But my understanding of vineyards is that they kind of appear by having a filtration and then changing the order of the simplices.
Yes.
And there you cannot have this like branching or merging behavior except merging into the diagonal.
Okay. Mm-hmm.
But for the graph code, you can have like one point branching out into 3 other points of the diagonal.
Yeah, because it's like a vector mapping. I was asking not really about for fear that you were already repeating something, but also because it is interesting to have algorithm to compute vineyards. And I was maybe wondering if the graph code could be adapted to have a vineyard decomposition or something like this. But as you said, since a branch for graph code can branch and merge, maybe that is not possible. But it's interesting. I thought it was interesting to think.
I mean, I don't completely understand what you mean by vineyard decomposition.
Mm-hmm. So a vineyard is made of vines, and each vine, the intuitive definition is that, which is the definition you can find around, is that a vine is basically the path made by one point in the persistent diagram follow across in different degrees or slices.
So you basically want to find a one-to-one matching between consecutive. Yes. Oh, I see. Yes, I think this is done in like multi-parameter persistence images.
Okay.
That they take like the fibered barcode and then they apply this vineyard decomposition to connect them.
Yes,
but
yes.
I don't know from the top of my head.
No, it's okay. Because the point is that when you have multiple, as you were saying, vineyards are made of swapping. And when you have too many swaps, this becomes computationally unfeasible. Even if the algorithm per se has only linearly many updates for swap, when you have too many swaps, this is just too much. So I was maybe thinking, okay, maybe we can use the graph code to get intuition about an alternative method to compute vineyards, but maybe not. It was just a thought. Yes,
that's certainly something I've not thought about so far. But so the point of the graph code is that it's actually just an alternative representation of the persistence module.
Yeah.
So you kind of take the invariance. So what you get is actually the complete description. That was the initial idea.
Okay, I understand. Thank you so much. Oh, Bianca has a question. If you can, please unmute yourself. Otherwise, just no. Bianca disappeared.
No, okay, I lowered the hand. Did you also do experiments, like you said, you did the synthetic data with homogeneous noise and then also practical data? Did you do the practical data with non-homogeneous density in the noise?
So you mean if we put density in a non-homogeneous way?
Exactly, yeah.
No, I think so in all the instances, I put the density in a homogeneous way, but what I did in creating these instances, I varied like the level of density. So also that so the density of the noise is also random for each instance. But I did not try in homogeneous density, but we applied it also to other instances. For example, for this multiparameter vectorization methods, the most prominent data set to test these vectorizations and the learning from these vectorizations is, at least as far I can tell, this so-called TU data sets. There's like a data set of various graph instances, and people compute some kind of bifiltrations from these graphs. And I think they get the bifiltration by using some kind of graph curvature and some kind of spectral filtration from the graph. And we also tried the Graphcodes on this instance, and it was kind of on par with the other methods, but it did not outperform them there. But the problem
but it didn't get worse than the other methods.
It depends. So if you look at the results from them, it's very random. So some methods work better on some instances, and some methods work better on other instances. There were some instances where the Graphcodes did quite well. I think they were not the best ones, but they did very well. And as others, they were very bad. So it's a little bit, these results are a little bit undecisive. Also, if you look at the standard deviation they put for the results, so most methods are within the standard deviation of the other methods. Like speaking of the average test set accuracy they put. So
and is it unclear what makes it go bad or good?
I mean, I would say that it's just unclear why topological descriptors are the right thing to apply to these instances. So we actually don't understand how people got to these instances. So why people test the multiparameter persistence on these instances. One of the reasons might be that these graphs are actually not that big. And like some of the papers are already a little bit older. And I think like 5, 6, 7 years ago, computing the 2-parameter persistence on like big point cloud datasets, as the ones we applied it to here with the synthetic dataset, was actually challenging. So maybe they applied it to these graphs because they're small, but I actually don't know.
Fair enough.
And the problem is that there are not that many established test datasets for multiparameter persistent homology.
If is okay, Bianca, do you have other question?
No, thank you.
Okay, perfect. I see Dave unmuted. Okay, perfect. You can go ahead, and maybe this is the last question for the recorded part.
So my question is, the examples you showed us were all for dimension 1 persistence. Did you try examples with dimension 2 persistence for shape data?
No.
In 3 dimensions?
Not so far. Okay. So we would like to conduct more experiments, but one thing that is actually a problem is, so if you go to like higher dimensions, you kind of need to sample more points to kind of get to capture the shapes. And it was already a little bit costly for many of the methods to actually compute the vectorizations. So with more time, we could have, of course, do it, but it will already get challenging for some of the vectorization methods. I think for one of the vectorization methods, my computer ran for 5 days to compute it.
Good. Thank you. That's good.
But of course, more more extensive testing has to be done. And hopefully will be done in the future.
Okay, thank you very much, Florian. That was a lovely talk. And yes, if people want to clap more, they can clap. In the meantime, I will stop the recording.
Thanks for inviting me.